Okay, so what I'm going to do is just pretty much imagine we just had a 5-minute break from the last lecture. Okay, so just to go back over the last lecture, I looked at sort of what you did last term in terms of rotation, scaling, transformation, and also some basics regarding vectors. So that was all last lecture. Right, is this new to you? Have you ever seen anything looking like this, or anything with the words graphics rendering pipeline? Is that new? Doesn't matter if it is. Okay. Essentially, what this is sort of a flow diagram, which is the processes involved in taking a virtual world and putting it on your computer screen. Okay, and we often call it graphics rendering pipeline. If you Google this, you'll see various different forms of it. Some have fewer sort of boxes and processes than in this one. The reason I'm showing you this is I want to show you where you're up to in terms of the units and what we've got to do for the rest of this term. So this is involved in creating a virtual world and going from your primitive objects. So when we say primitive objects, we mean if you did assignment 5, it means take down from cubes, pyramids. If you've got computer game barrels or a house or any object which goes into your virtual world, and you have to go all the way around these processes, and eventually it gets outputted onto the display. Okay, so we start off with the object space. These are objects, usually 3D, which are defined in their own space, and what you do is you use scale, rotation, and translation operations on each individual object, and you build your world space. Okay, so your world space, imagine Lego bricks. Each of your Lego bricks is an object, and then you're building your Lego, whatever it is, and you create your world space. Once you've got your world space, what we want to do is align it to the viewing vector. Okay, so you're in your world space, imagine you have a camera and you're pointing it in a certain direction. What we do is we rotate our whole space so that the direction you're pointing the camera in corresponds to the z-axis. So you're always looking straight down the z-axis. And that involves rotation, okay, rotation and translation operations. And this gives you what we call the aligned world space. Okay, it's the same, haven't done anything to the world space, all we've done is rotate it, move it around, so that the camera position is at the origin, and the direction the camera is pointed in is directly down the z-axis. Remember, z-axis on the left-hand coordinate system, z-axis is pointed into the screen. Some textbooks in websites have the z-axis pointing towards you. Doesn't really matter if you've just got a negative z or a positive z. I mean, the mathematics is still the same. Okay, after you've got the aligned world space, you then project onto a viewing plane. Now, this is my screen. It's only 2 dimensions. If I had a 3D world, I've got to somehow squash that 3D world onto a 2-dimensional plane. And that's what this process does. Okay. So I've gone ahead of myself a wee bit. I've stepped through these. So this is the object space. Okay. What I've got here is x, z, and y coordinates. The subscript O just stands for object. We normally don't put these there. And these are a couple of examples of primitive objects. I've got like a little house or a sort of tower there. Okay, so each object is defined, so usually the base is at the origin. What this means is we can then scale our objects, we can rotate them around, and then we can move them easily. Okay, so that's your object space. When we're defining objects, it helps to do it in a consistent manner. Okay, so we need 2 things. We need our position of our vertices of our object, and we also need information on the faces of the object. Okay, so the simplest kind of object is a cube. So you can see here I've got a cube. Now it's quite difficult to actually draw 3D objects on 2D. So I try my best. But, so here we've got a cube. Okay, it has 8 corners to the cube. So therefore we have our 8 vertices. I've labelled them B1 through to B8. Now, of course, a cube has 6 sides. So we have 6 faces. So 8 vertices and 6 faces. Okay, one way of thinking about it, especially in 2D, is if you sort of flatten out. Imagine, I don't know whether you did these when you were younger, you had these sort of cardboard things to create 3D models, and you use sort of glue and cut them out and stick them together. Okay, so that's sort of what I've done here. So imagine this square, that's our front edge. Okay, and that's corresponding to this edge. Okay, the side here, which is B2, B3, B7, and B6, is that right edge, and so on and so forth. So they sort of, that's the plan, that's the pattern for that cube. Okay, well you see here the front edge is defined by B1, B2, B6, and B5. Okay, so oh, actually I've got those wrong. Oh, ignore that. I think that's not corresponding to front edge. 1, 2, 3, 4. Oh, yeah, I think I got that slightly wrong. Ignore that. Anyway, so the front edge, if this was the front edge, this should be V1, 2, then 6 and 5. So I've got a little bit of a mistake there. Okay, so ignore the actual values. The point being is each of these rows of this space matrix corresponds to what vertex the face is defined as being. We've got 4 columns, so each face has got 4 points. Okay, going back to the vertices, here we have our vertex array. This is 4 rows because this is X, Y, and Z, and the bottom one is just 1 for homogeneous coordinates. Okay, so the first row is all your X coordinates, Y coordinates, and Z coordinates, and each column corresponds to each of those points there. And if I had the faces one correct, okay, those 2 would be enough to actually define that cube. Right, so the world space. So we've got objects. So that's our objects. What we do is we take the objects and we place them in the world space. So I've taken 2 of the house objects and one of like the tower object. I've used translation, and actually don't think I've used any scaling there, but it's just placed. And you'll have thousands of these in a virtual world, in practical, real virtual. I say real virtual world. In a real example of a virtual world, like a computer game, you'll have thousands of objects in the world. Okay, and this is placed within your world space. Next step on the graphics rendering pipeline aligns the viewing vector. So let's say we have a camera position at this point P, and we're pointing the camera to what we call the center of view, which is C. Okay, so that will give us some direction, D. Okay, and what I want to do is I want to align the world space so this position is at the origin, and this vector D is pointing along the z-axis. Okay, so the first thing we do is we translate all of our points in the virtual world. So there might be thousands of them. We translate them all by minus P. Okay, so we're moving them all by minus P, which moves your camera to the origin. The next step is we rotate around the y-axis so that our D vector is now in the ZY plane. So this sort of dashed vector is where it used to be, and we rotate it around the y-axis so it's now in the ZY plane. Oh, okay, so your D vector is in the ZY plane, but it's still not pointing along the Z axis. Okay, so now we need to rotate it around the x-axis. Okay, so we now need to rotate it around the x-axis over d points along the z. Okay, so there's three transformations. We translate, so it moves p to the origin, so we translate by minus p. We rotate about the y-axis, and we rotate about the x-axis. So that's what we call our alignment transformation. Translate, rotate about y, rotate about x.
Since the objective is to start from the origin, why not start and put a camera at the origin?
That's a very good question. Okay, so the question is, okay, well, if we're moving to the origin each time, why don't we just have the camera at the origin? What if we want to move the camera? What if we want to move around our virtual world? Our camera's moving. Once the virtual world is defined, we don't change it. So as soon as the virtual world is defined, we don't change it. We only align it each time. So that's our alignment transformation matrix. Notice the order. Going from right to left, translate, then rotate about y, then rotate about x. This is our coordinates of all of our points in our virtual world. There might be millions of those. So it'll be 4 by however many points we have. And this is an important thing to note at the bottom. It appears to the viewer that you're moving around your virtual world. So if you play a computer game, it's 3D, you're moving around it. What's actually happening is the virtual world is moving around you. It's kind of like optical, not really an optical illusion, but that's what's happening. So you move the virtual world, you don't actually move the camera. Okay, how do you calculate that alignment matrix? Well, what I've done here is, because it's quite difficult to actually draw 3D on 2D, so imagine we're looking down the y-axis. So we're looking right down it. Okay, the first thing we want to do is rotate this vector so it's in the the YZ plane. So we need to rotate it around the y-axis by this angle theta. Okay, and that's we saw earlier on, or last term as well, that's our rotation matrix for rotation about y. So we need cos theta and sine theta, or do we? Okay, I keep saying cos and sine are quite expensive calculations. Well, what we can see here is that we have a right angle triangle. So this is our angle. dz must be the adjacent side. dx is the opposite side. And the hypotenuse is what I've called d1, which is Pythagoras' theorem, dx squared plus dx squared. Okay, so cos is adjacent, which is dz divided by hypotenuse, and sine is dx divided by hypotenuse. So instead of cos theta and sine theta, I replace those with those ratios. And that's our rotation around y matrix. We could do similar for the x, rotation around the x-axis. Okay, so this time we're looking along the x-axis, and so this is our dashed sort of vector. That's what we have after the first rotation. Okay, so this is z and this is y. We want to rotate it 5 degrees, or sorry, 5 radians. So we end up with a vector along the z-axis. So again, having a right angle triangle. In this case, the adjacent side is d1, which was d1 was the hypotenuse from the previous rotation. Okay. Opposite side is dy, because we haven't sort of, in the previous rotation, we didn't move it up or down, we just rotated it horizontally. d2 is the hypotenuse, that is the magnitude of our original vector. Okay, so the d2 is the magnitude of the original vector. So cos phi is adjacent over hypotenuse, so d1 over d2. Sine phi is opposite, which is dy over d2. Plug those into the x rotation, and you get Rx. Okay, do all that, and this is what you end up with. Okay, so that was all assignment 4 from last term. So what you end up with is you end up with your camera position at your origin. And this is what we call the aligned world space. This is the world space which is aligned to that viewing vector. You're looking, this is my attempt at drawing an eye, along the z-axis at your virtual world. Okay, so that's the aligned world space. Okay, so we've got the objects, we've built your world space, you've aligned it to the viewpoint. Next thing we need to do is project it onto what we call a viewing plane. This is so we can actually see it. 3D displays haven't been invented yet, so we're still on good old-fashioned 2D. So we need to project onto a 2D viewing plane. That's what we mean. Okay, so this is your aligned world space. Imagine I've put a plane between these buildings here and the camera position, and that plane is parallel to the X and Y axes. Okay. And what I'm going to do is I'm going to project these buildings onto this 2D plane. Okay, you notice I've given the axis labels of XS and YS for screen. That's denoting screen space. So that's our next step. How do we do this? Well, I'm going to sort of, again, take it down to 2D just for ease of sort of drawing the diagrams. Okay, so this is my aligned world space. Get rid of that viewing plane. This is my aligned world space, and let's say we have a single point in the world space. So here is the z-axis. So the camera is here looking along the z-axis. Okay, so we place the viewing plane at a distance f along the z-axis. So that distance there is f. What we do is we draw what we call a projector. There we are, a projector from the origin to our point in the world space. Where that projector crosses the viewing plane, we have our projected point. That's all we're doing. Okay, and that's how we project something in 3D space onto our 2D viewing plane. Okay, so how do we go from 3D coordinates, 3D world space coordinates to screen space coordinates? Well, if we take this diagram, this is the same diagram from before, and I've labelled O for origin, A for this point, B for this point. Now the triangle OAPS is similar to the triangle OBP. Similar means it's the same shape, just side up or down. So that means the angle here is the same for both triangles. Quite easily to see from that diagram. If that's the case, then the x coordinate, so remember this is the x or y axis, this length here, P minus B, which is x or y, divided by B minus O, so that's your z value across there, that's your x value. So x divided by z is the same ratio is xs divided by f. So that distance there is f, that distance there is xs. So xs over f is the same ratio as x over z. Rearrange to give xs, and that's your screen space coordinates. So you know x, you know z, you choose what f is. That f is how far in front of you your viewing plane is. Do the same for y, and you get your y coordinate. So we can express this as using the matrix equation. So this 4x4 matrix, this is what we call the perspective projection matrix, multiplied by your aligned world space coordinates. So this is after you've aligned everything. Okay, and this is what results. So this is your homogeneous screen space coordinate. We want Cartesian, so we divide throughout by z over f. So we divide x, y, and z by z over f, and we give our screen space coordinates there. Okay, so again, it's a matrix multiplication. So You multiply all your aligned world space coordinates by that matrix. Don't forget, you've got to divide your x, y, and z coordinates by whatever the fourth row is to give you your screen space coordinates. Okay, that's what you get. This was a screenshot of my answer to assignment 5. Just want to show you that working. There we go. No, is it going to work? It's working incredibly slowly. Don't know why it's working slowly, probably because I'm doing recording it as well. So this was my solution to assignment 5. My virtual world, I've got the camera on like a helicopter, so the camera's orbiting around my virtual world. So for each frame, I'm aligning the virtual world to the direction of view vector, and I've used perspective projection. So you can see here, this part of, let's say this is a church, the nave of the church, the front of it is bigger than this house back there, because that's in the distance. That should be smooth, but I think it's because I'm doing screen recording at the same time. Okay. So this is all sort of just recapping from last. It's not letting me cancel that. Oh no. Stop. Okay, this, I'll try and crack on. Right, that was all last term. Okay. I'm like an hour and a half into my lectures, and I'm only just up to this term. Okay, so we've got all this to do. So we're up to screen space. What we're first going to, for this week, well, the remainder of this week and most of next week, we're going to be looking at what we call clipping. Now, essentially, clipping, there's only a finite area which you can see in a virtual world. Okay. Anybody tell me what's happening behind you without turning around? Sorry?
People are staring again.
Behind you guys? Yeah. Back row, what's happening behind you guys? So if I was to tell you there's a dragon flying out the back there. Essentially, that's what clipping is all about. You can't see, you've got a field of view, you can't see what's going on behind you. It's even worse when looking for a screen. When you're looking for a screen, you can only see a finite amount of your virtual world. And this is what we call a viewing frustum. Okay, so that's your eye. This square here is your screen, your computer screen. Okay, but if I do the projectors between the edges or the vertices of the screen and project out beyond, anything within this sort of volume here should be able to be seen. What if it's something outside? What if it's something over here? It's not going to be seen. So we're going to ignore it. We're going to clip it. Okay. So what we do is we actually take the screen space coordinates and we transform them so that the visible region, which is this sort of volume here, is a unit cube. Now by unit cube, we mean that our x, y, and z screen space coordinates are in the range -1 to 1. If I have time, it'll probably be the next lecture. I'll show you how to do that. Any polygons which are outside of this volume gets ignored from now on. Any which are partially outside are clipped, means we cut them. So we cut them so that we only cut them to the edges. So here we have an example. So this is a virtual world. Okay, what I've done is I've placed the camera there at 0, 0. I've placed the screen there, and I've sort of tried to plot the viewing frustum. Okay, so there's my virtual world. And what we do is that viewing frustum, which is like a cone, sort of like a cone shape, well, not quite, but, and I've transformed it so it's then in a unit cube. And you can see parts, for example, this part of the house should be cut. Okay, we don't want to see that bit. And there's a bit of the church there which should also be cut because it lies outside of our visible area. Okay, so that's what happens when you clip it. Okay, you notice just clipped. to there. Okay, so that's what we're going to be looking at this week. In a couple of weeks' time, we're going to be looking at removing hidden surfaces. Up until now, we've been dealing with what we call wireframe graphics, very old school, very sort of 80s and early 90s. If you ever play games from 3D games from those regions, okay, that's what we had. In the 90s, we started looking at ways to get rid of hidden surfaces. So these objects were transparent, but we could, by only plotting the surfaces which you can see, suddenly they become a bit more realistic and a bit more solid. Okay, so that's going to be your assignment 7. So assignment 6 is clipping. Assignment 7 is hidden surface removal. Here's an example of an object, teapot. Okay, so there's a teapot, which what I've done there is I've drawn it using all the polygons in the object. And what I've done here is imagine if I'm looking at the teapot from this direction, I won't be seeing what's on the back of the teapot. So I've only drawn those polygons which I should see. Now, if I was to view the teapot from over here, it would look solid, but I'm only drawing half of it. Okay, so that's a technique called back-face culling. Dead easy to do, by the way. That's your assignment 6. Not on a teapot, it's only on doing it on a tetrahedron object, but it's dead easy. Okay, so that'll be, talk about the teapot. This teapot has a sort of special, this is a sort of special object, and it actually appears, it's a common reference object for graphics, and it appears in every Pixar film somewhere. Every Pixar? Yep, somewhere hidden. It's in Simpsons. Have you ever seen The Simpsons when they go into that 3D world? Yeah, teapot's in there. Okay, it's like an in-joke in graphics. That's the original Toy Story. Have you ever seen that? From 1995. When were you guys born? 1995. Wow, that makes me feel old. Anyway, so from 95, there's Newell's teapot, or what we call the Utah teapot, and there's Buzz Lightyear having tea with it. But yeah, it's in every Pixar film, somewhere, hidden, tiny, could be in the distance. It's in, I know for a fact it's in Star Wars Episode 3. You ever seen Star Wars Episode 3?
Literally just watched it.
Well, not now.
Oh, no, I'm good.
In Star Wars Episode 3, there's a fight at the beginning. It's like, Obi-Wan Kenobi is flying through, and there's an explosion. And from the explosion, there's this kitchen sink object which gets flying off. And anyway, heaps of boring, so I'll carry on. Okay, so that's removing hidden surfaces. Then we come on to lighting. Okay, lighting's actually. I say lighting. I could turn the lights off. You see that bit better. Lighting's actually very, very difficult. The lighting models we're going to be looking at are what we call direct lighting models. There are 2 types, direct and global. I was playing a computer game last night, and the lighting model uses a volumetric shader, which means you could have light rays coming in, you could have shadows and all that. But lighting pretty difficult. Okay, so we'll be looking at direct lighting models. Okay. What else are we going to be doing this term? Rasterization. At the end of the day, your computer screens, your mobile phone screens are made up of lots and lots of little squares, and those squares are coloured in a certain colour. And those squares are called pixels, and a collection of pixels is called a raster. And so the raster, the screen which you're seeing here is actually a raster array, lots and lots of pixels. Okay, I take Olaf. What I've done here is I've re-rendered him so he has less pixels. So that's quite a high pixel density, so the pixels are very small. Now, re-rendered him to a low pixel density. If I zoom in on his eye, you can see how that image is made. Okay, so we'll be looking at rasterization as well. And that's your assignment 8 to reproduce that. So what we have here is 200 by 200 pixels. I'm drawing a star and a circle in it. What else are we going to do? Texture mapping. That's my cat. Just needed a picture. So I've got a raster of my cat. Okay, and what we can do is we can map each pixel in that image to a point on a polygon. And as we move the polygon around, the image should move around with it. Yeah, that's called texture mapping, which we'll look at. You won't be asked to do this in an assignment, by the way. It's quite involved. We're not trying to scare you off here. Okay, so that's, and then that gets sent to the display, and the display prints it on the screen. Okay, that is done in a modern computer game system or something like that, 60 frames a second. 60 times a second you've got to do for all of this. Well, actually, from this all the way down a second. Which is why graphics applications are very, very computationally expensive. It's why modern computer systems have got an expensive graphics chip in them. In this sort of process, you're doing all this, we haven't considered mechanics. We haven't considered any physics which is going on. We haven't considered collisions, so all the stuff you did last year about collisions and things bouncing off. AI, if you have a computer game, you might have non-player characters acting realistically. Other human-controlled characters, so you may be playing against somebody. There might be bandwidth issues, you might be playing on the internet against somebody. All of this takes place 60 times a second. So it's quite impressive when you think about that. Oh yeah, a couple of other things we're going to be looking at. Bézier curves. Okay, these aren't really related to virtual environments, but they are a common graphics application. Essentially, they're parametric polynomial curves. So whenever we want to draw a nice smooth curve, okay, this smooth curve here is defined using just these 4 points. And we can draw these, and you can make loops and curves and things like that. Draw 3D surfaces, and it's used extensively in graphic design. So, for example, a classic example is car manufacture. Okay, that's where Bézier comes from. He worked for Citroën, I think, and he invented the curves. Okay, this is your assignment 9. Okay, there you are. Creating the logo, university logo, and that's this sort of arrowhead here. That's defined using 8 curves. So each of those curves just uses 4 points to draw that. Now that's an object, and what I've done here is I've translated and rotated it. So that's my single. So to draw this, all I need to do is define that. That's a bit trial and error. That took me about half an hour. Okay. Apply rotation and translation. So I've copied it, moved it, rotated it, then I just filled it in, and you get the logo. That's your assignment 9. And finally, pretty pictures, fractals, which we sort of mentioned this morning. Okay, fractals are shapes which are generated using a recursive set of rules, mathematical function normally. Fractals have a self-similar property. Self-similar means the basic shape of a fractal is replicated within the fractal at different scales. Okay, so have you seen this one before? Anybody know what that's called? It's called the Mandelbrot set. It's quite a famous one. If you Google or YouTube Mandelbrot set, there's loads of funky videos on it. What you can do is you can zoom in. So I think what I've done here is I've zoomed in on this portion, okay, and I can keep zooming in, and I'll get lots of mini Mandelbrot sets in there. And I can zoom in on those mini Mandelbrot sets, and you get other ones. Okay. Well, this self-similar property is shared by landscapes. Believe it or not, landscapes, hills, mountains have a fractal property. And so your final assignment is to write a landscape terrain generator. So this is what I've done. This is a fractal. Okay, so this has my landscape, and I've also put on like a flat plane to sort of resemble water. And there you go, that's the fractal landscape. That's quite easy to do, by the way. It looks impressive, but all of these things are very doable. Okay, even though at the moment you might think, how the hell do you do that? I'll be teaching you all these. Right, that's what we'll be coming to do in term 2. Any questions on that? Really? Okay. Does that sort of seem okay, or does it seem daunting? Or?
I'm feeling that somebody like me, I haven't quite figured out the assignment 5 years.
Yeah.
How do I move on?
You don't. Each of these assignments doesn't build on from anything in term 1. Okay, so if you did sort of find term 1 stuff hard, the assignments are sort of all standalone. They don't build up on anything before it. So, for example, if I just bring up the let's have a look at some of the. Oh, I think my MATLAB is really slowing this down. Is it still going round? It is. Oh well. No, it's not letting me. Oh no, not that one. Come on, sorry about this. Give me 1 second. It's. Oh, this is taking ages.